before we move on from comparisons, I wanted to give you one more helpful rule of thumb to guide you. One of the principles that we discussed in the last video was that often you want to look at which terms are growing the fastest, and sometimes that's obvious, but that's not always the case. And so what I want to talk about in this video is how do we tell whether a term is growing faster than some other term? And what I'm going to give you is an approach and then a hierarchy that you can use as a general guideline for comparing the rates of growth of different functions. Okay, so first the principle. The way to tell if two terms, and I'm just going to call them an and bn, if an grows faster than bn, and I'll put much faster, is to check if the limit as n goes to infinity of an over bn is infinity. Okay, so if I want to compare two terms an and bn, we would say that an grows much faster if when you take the ratio of the two quantities, you get infinity. Okay, so there are lots of functions that you might want to compare. For example, suppose you want to know which grows faster, square root of n or n. Well, we can compare square root of n over n as n goes to infinity, and you would see that equals, well, let's see, that's the limit of, you could cancel out a factor of n to the 1/2 from the denominator and get 1 over square root of n, and that gives you 0. And if we took a reciprocal, if we did the limit as n goes to infinity of n over root n, we would get limit as n goes to infinity of root n, which is infinity. And so you'd see that the n grows much, much faster. Okay, so n, we could say, is much, much bigger than root n for large n. And then when we're trying to choose a comparison, often it helps to have some intuition. If we know how a series involving n behaves, that could tell us something about how the corresponding series with root n would behave, and vice versa. Okay, so that's the principle. If you want to compare two terms, look at the ratio and take a limit as n goes to infinity. And if you get infinity, you know the numerator is bigger. And if you get 0, then the denominator is bigger. Okay, so there are lots of different types of functions you might want to compare. But let's look at a few examples. So first of all, often we'll have constants that are floating around. And the claim is that that is going to be smaller than things like the log of n, which is in turn going to be smaller than something like the n raised to the k, where we're going to assume that c is greater than 0, and 0 is less than k is less than 1. So this is some exponents. The exponent of n here is a number between 0 and 1, which means this is something like a square root of n or third root of n or something along those lines. And that in turn is going to be smaller than just n, which is smaller than n times the log of n. And that is going to be even smaller than n raised to the 1 plus c. And we could continue going down the line. That is going to be less than c to the n. And I ran out of space, so let me just slide that over just a little bit. C to the n is less than n factorial, which if you recall, that's just n times n minus 1 times n minus 2 all the way down to 1. And that in turn is less than n raised to the n. Okay, so there's a whole bunch of different functions that we've compared, and I basically listed them off from smallest to largest. We have constants, logs, powers of n that are between 0 and 1, n to the 1, n log n raised to a power that is bigger than 1, exponentials, factorials, and lastly, n to the n. And you shouldn't just take all of those comparisons on faith. You can actually check that the order of each of those is correct by taking limits. But we won't check all of them for the sake of time, but let's look at a couple of them. All right, so let's verify first of all that n to the k is bigger than ln n. okay, where k is between 0 and 1. And as we said earlier, we can compare the rates of growth of those by taking a limit of the ratio. And so we'll put the n to the k on the top over ln n. And as n goes to infinity, notice that looks something like infinity over infinity, because both terms are going to grow. And that suggests that we can apply L'Hopital's rule here. So we'll take the derivative of the top, which would be k times n to the k minus 1, all over 1 over n. And that 1 over n, we could cancel out by multiplying by n. And so if we multiply that on top and bottom, we'll have limit as n goes to infinity of, let's see, the bottom is just going to be 1. And now we have n to the 1 and n to the k minus 1 multiplied together. We'll notice the minus 1 and the plus 1 in the exponents will cancel. We'll have k n to the k. And since the exponent is positive, that has got to go to infinity. So the fact that we got infinity means the original numerator is bigger, as we claimed. Okay? All right, let's do another one. Let's look at the limit as n goes to infinity of n factorial all over n to the n. Okay, let's compare those two quantities. And the claim is that n to the n is actually bigger. And in fact, just to keep it consistent, I'll put the n to the n in the numerator. It doesn't really matter, but it'll make it more consistent with what we did in the previous example. All right, so the claim is that n to the n is the bigger one, and if it is indeed much bigger, then we should get infinity here. How can we convince ourselves of that? Well, let's think about what n to the n means. That's just n times n times n, a total of n times, right? That's the numerator. And n factorial means n times n minus 1 times n minus 2, all the way down to 2 and 1. And notice there are also n factors right there. Okay? And if we look at all those factors, notice we could group terms together, and we'd see that each of those individual factors is going to be 1 or bigger. And this last one is actually just n. So we could say that that limit must be greater than the limit as n goes to infinity of just n over 1, because again, this is the one on top was just a bunch of fractions that were all greater than 1 multiplied by n over 1. All right? And this limit, it's very clear. Limit as n goes to infinity has got to be infinity. And so as we hoped, n to the n must be bigger than n factorial. And we could do one more. Let's look at c to the n and n factorial. And the claim is that n factorial is the bigger one. Again, I'm using the double greater than sign to mean that n factorial is not just bigger, but it's bigger in the long run when n is large. And so we'll look at the ratio of these two things. All right, and so we'll have n factorial on top and c to the n on bottom, which can be written as the limit as n goes to infinity of n times n minus 1 times n minus 2, all the way down to 2 and 1. And again, there were how many factors? N. And then in the denominator, we have c times c times c, with a total of n factors. Well, if you think about this, although we can get group terms together, since we have the same number of factors on top and bottom, and depending on the value of c, we may find that some of those factors are less than 1, but eventually we're going to find one where the term on top is bigger than the c, right? Because n is going off to infinity, means eventually these terms in the numerator get as big as they want, whereas c is not changing at all. And so what we can say is that this has got to be greater than n over c, because if you think about all this other stuff, there's a whole bunch of factors that are greater than 1 there. And so that's definitely got to be bigger than 1. And like before, that's an easy limit. It's got to be infinity. Okay, so these examples, we worked through these limits in a way that was not entirely rigorous. The goal was not here to come up with a completely perfect proof, but to give you the intuition for why it is that we have this hierarchy of functions. But now that we have that, we can use that as a guide when we're trying to choose what to compare to. So I would recommend putting this in your notes and circling it, boxing it, whatever it takes to make sure that you've remember to take a look at that, because we are going to want to reference that from time to time. All right, so let's apply that now to a couple of examples. Let's look at, first of all, the series where the terms are, how about 2 to the n over 3 to the n plus, how about square root of n? Okay. So we'd like to determine if that converges or diverges, and because we have a sum in the denominator, it makes sense to try to think if maybe we could throw away one of those terms in the sum to get a simpler expression. All right, so let's go back up to our hierarchy here. We have 3 to the n and root n. Which one is going to be larger? And if you look up here, there's where our root n would be. That's n raised to some power, and 3 to the n would be over here. It's some constant raised to the n. And so it's clearly got to be the larger one. And so that suggests that an appropriate comparison would be something like 2 to the n over 3 to the n, or just 2/3 to the n, which is the same. And this looks like a geometric series. The sum of 2/3 to the n has got to converge, since the ratio is less than 1. All right, and so now we could try to use maybe a direct comparison or a limit comparison. Either one would be an option. Let's go with the limit comparison. So let's look at the limit as n goes to infinity of 2 to the n over 3 to the n plus root n over 2 to the n over 3 to the n. We could multiply by the reciprocal here. And what we'd get is the limit as n goes to infinity of, let's see, 2 to the n times 3 to the n. That's actually the same thing as 6 to the n. On the bottom, we'll have 2 to the n times 3 to the n again, 6 to the n, plus 2 to the n root n. And on the bottom, we'll just have 1. Okay, so that looks a little better. We're going to keep going here. It looks like we're still going to have infinity over infinity if you plug in infinity for n. However, if we multiply by 1 over 6 to the n, we'll be left with 1 over 1 plus, let's see, 2 to the n over 6 to the n would be 1/3 to the n times root n. Or better yet, we could write that term as root n over 3 to the n. And if we could figure out what that little fraction approaches, then we would be in good shape here. So let's go back up to our hierarchy again and remind ourselves of what we claimed. We claimed that n raised to a power, so square root of n would be an example of that, is much less than an exponential using a positive number 3. Okay? So, oh, by the way, this should be c greater than 1 there. If c is less than 1, then that's actually going to shrink over time, and so that would not be true. So c has got to be greater than 1 for that to be true. And so, in fact, let's make that a little clearer here. Let's choose p to be greater than 1, and let's just make that p to the n. All right. So it doesn't change our answer to this problem, but we should be specific there so that that statement is actually true. Okay, So now that we've got that information in place, we know that this term, the exponential, grows much, much faster than the square root. And if we look at this, that means that for this term, the denominator grows faster, which suggests that that has to go to 0. So the hierarchy can also be a way of giving us a shortcut to evaluate certain limits. If you know which function grows faster and you have a fraction with one function in the numerator, one in the denominator, you can easily jump to, well, the limit must be 0 or infinity. Again, if those are different terms in our hierarchy. All right, and so that tells us our limit is 1. And if the limit is 1, then the sum of an must do the same thing as the sum of bn. So the sum of an must converge because the sum of bn converges, and an over bn approaches 1. Okay, so our hierarchy guided us in choosing an appropriate comparison. Let's quickly do a couple more examples. Let's consider an is equal to 1 plus minus 1 to the n over n squared. This one's a little bit tricky. What I want you to notice is that this minus 1 to the n alternates between 1 and negative 1, 1 and negative 1. If we have a negative 1 here, then that means the numerator is 0. And if we have a positive 1, then that means the numerator is 2, right? So we can say that an is definitely less than or equal to 2 over n squared, and it's greater than or equal to 0 over n squared. Okay? All right. Well, again, thinking back to our hierarchy, 2 definitely is smaller than n squared, so the terms go to 0. It doesn't tell us about convergence or divergence, but it does give us the chance that it could converge, because if we get terms that were going to anything other than 0, the nth term test would tell us that it diverged. But this suggests that that might be a good comparison to make. So let's look at the limit. Well, in fact, let's just see if we can use that result. What do we know about the sum of 2 over n squared? Well, that's the same thing as 2 times the sum of 1 over n squared. And that's a p-series. And we know for a fact that that converges. And so if that converges and the individual terms of this original series are smaller, then the sum must, of course, be smaller as well. And so it must converge too. All right, so this is a smaller than something small scenario. We know that this series converges. The one that we're interested in is smaller, so it must be convergent as well. All right, last example. Let's look at an equals 1 over n factorial. We'd like to determine if it converges. And the problem is, I don't think we've done any series like that before. So, doesn't look like we can simplify that expression much beyond what it already is. And it's not a p-series, it's not a geometric series, it doesn't fit into many of our traditional categories. So we need to think about what we should compare it to try to answer this question. Now, if we think back to our hierarchy, I'm going to scroll back up here. Notice n factorial is really, really big, right? It's bigger than exponentials. It's bigger than powers of n, like n squared or n cubed. And so what that suggests is the denominator is growing really, really fast. And so the fraction must be getting close to 0 really, really fast, which suggests to me this converges because an goes to 0 quickly. All right, so knowing how fast different terms grow can help us make a good hypothesis here. And we also know, based on what we just said, that this is greater than, say, well, n factorial is greater than n squared, which means 1 over n factorial is less than 1 over n squared. And so the sum of 1 over n factorial must be less than the sum of 1 over n squared. Well, we already said in a previous example, in fact, we've said this many times, that the sum on the right converges, and so this must converge as well. All right, so I hope that you find this hierarchy of functions helpful for giving you sort of a starting point for thinking about whether a given series is going to converge and what you might want to compare it to. This is something that you may want to commit to memory just to give you some intuition as well as potentially some shortcuts when you're trying to get started on some of the homework. All right, that'll do it for this unit, and in the next batch of videos, we will look at some more practice problems and just get more comfortable choosing the right method for a given problem and applying methods to determine whether a series converges or diverges.